So before we start, what I want to do is I want to walk you through the material that we have covered. And you may be surprised on the amount of material that we have covered. And just to wow you, I'm gonna share something with you. So I hope you can see my screen. I want you to go to Canvas, and there is MATLAB quadcopter simulation that I have uploaded, the last zip file. I want you to go unzip that file. And if you go and unzip, there is a folder which is called demo files to share. Grab that folder and expand it on your desktop. Super important. Then go to, can someone guess what I'm going to do next? Go to MATLAB. Online students, can you see my screen? So everyone, please go to the demo files to share folder. Quickly. Are you ready to be amazed? Okay. Now, what I want you to do is, online students, there is something called as BH startup 6 DOS.m. Okay, somebody from chat window. Yeah, okay. So just click that. And then click run. And what happens? Boom. You get a knob. Did you get that knob? Online students, did you get this knob? If you are not seeing this knob, then go to system check. For this entire project to run, these are the toolboxes that should be installed. And if those toolboxes are not installed, your demo, thing will not run. If that is the case, go to MATLAB, home, go to add-on and get that add-on. Are you with me so far? Go to add-on and get that add-on. Where did Eric go? Eric supposed. Oh, you are here. Oh, sit, come here. Something in the front. Oh, I'm not flying it yet, so don't worry about it. If I start flying, then I will ask you. I will also ask Satvik to go back. Okay. Everyone, you see the knob with no? Yeah. So now you should go to demo. Believe you me, this is where we started, and that is where we are going to end. So what did we study? First and foremost, go to inertia. As soon as you go to inertia, you get a live script. This live script talks about the principal moments of inertia. So we have covered the inertia tensor. We have covered principal moments of inertia. And here is a nice sketch that talks about what do we mean by principal moments of inertia. There are two potatoes. One axis is aligned with the axis of potato, and the other axis is at an angle to the principal axis. Now this live script, what you can do is you can interactively run. So what that means is if you go down, you can actually click here, run selection, and the script would run onto the right-hand side. So you will see the equations for the moment of inertia. So if you want to find out the principal moment of inertia for an arbitrary object, what you do is you solve something called as the eigenvalue problem. And then that gives you the principal moment of inertia. And then if you go down, it actually talks about, it gives you a little bit more information about eigenvalue problem and what that is, what do we mean by principal moment of inertia. So this is talking about the frame. Another important point that I want to talk about, and I emphasize this when we discuss, look at the angular momentum equation. Angular momentum equation is the moment of inertia multiplied by the angular velocity vector. So basically, you can, if you want to try this in MATLAB, you can run this code in MATLAB. And there is an eigenvalue example. There is also another example. Remember the circle of vectors that I talked about, I cross j, j cross I is equal to k. All that information is encoded in the live script. And you can run these live scripts over here. And this also talks about the unit vector and other stuff. Are you with me so far? If you, have you opened this? Is it on? No.
Still extracted.
Yeah, that's all right. Now, if you don't like to watch this live script, actually there are movies also embedded. What you can do is you can go to reports, click on the principal inertia, and that will bring a PDF file that will give you the gist of what principal moment of inertia is, what is the application of principal moment of inertia, and all that stuff. Everyone understood this? So what else did we study? We looked at Euler angles and what Euler angles are. We talked about passive rotations. We talked about that the rotations are not commutative. So this script talks about what do we mean by non-commutative rotation? There is a movie embedded in here. So basically you are applying the same rotations, but in different sequence. Same rotations in different sequence gives you completely different result because the rotations are not commutative. Are you with me so far? Now, remember the transformation matrix that we talked about? This live script, you can actually encode, there is code in here that you can use to create the rotation matrices. Remember we talked about Z, Y, X, rotation about Z axis, rotation about Y axis, rotation about X axis. That takes us from the inertial frame to body frame. So that all the transformation is actually implemented in MATLAB. And some of you may ask me, why are we learning this again? It is super important because towards the end of this lesson, you can actually take the Simulink code, convert that into a C code and flash it onto a microcontroller. Before we do that, it is absolutely clear that we have an understanding of the math that is involved. And it's fun. So remember all these transformations that we talked about, the rotation about the inertial frame, then the rotation about the middle frame and the rotation in the body frame. You are welcome to run these live scripts, and finally you would get the relations that we derived in the third class. So this is done in MATLAB. And then we found out the relationship between the body rate and the inertial rates. And when the pitch angle is 90 degrees, the system becomes singular. So there is an example. If you want to run this, you can run the entire script in one shot, or you can run the section of the script one by one. And then what you can do is the next part, if you want to look at here, you can run this section. This section will take a MATLAB code, wrap it around in a Simulink block and give you the Simulink block. So basically you can run selection and it will open Simulink and then wrap it around and create a Simulink file that you can use for simulation. So for example, this Simulink function will actually implement that transformation. So give it some time, it will take some time, but this will come up. So you are welcome to try this. So we looked at the rotation transformation, and this is what's gonna happen a minute later. That we have this quadcopter model. It could be Parrot Bamboo, or it could be Tello, or it could be Parrot AR drone. What we have is, we have a Simulink block, and we are gonna get the roll rate, pitch rate, and yaw rate, or essentially the body rates, PQR, from the IMU on the drone. That information will get fed into the Euler angle transformation, and then we will actually use a direction cosine matrix transformation to find out the actual roll, pitch, and yaw. So please understand, this is what your code will look. So you will have Euler rates, and then you will have a DCM. So next part that we talked about is about the derivatives, or how do we actually find out the angular velocities. For finding out angular velocities, please understand a simple structure is you have the yaw rotation, pitch rotation, and roll rotation. So we talked about those. We also talked about the transformation from the inertial frame to body frame. Now here, what is happening is, the key concept is, how do you find out the derivative of the rotation transformation, because the angles are also changing. And why is this important? This is important because when we apply the Newton's laws, equation of dynamics, we will have to use this information. And this comes with the cross product. So I would encourage you to run this script, and you will see the cross product of transformation. And then finally, you would see the Simulink implementation. This implementation is gonna go and sit in the drone. So please read through that and understand how this implementation is done. And if you really want to see the PDF document that describes this, either you can actually open the derivative.pdf, task.pdf, or you can just go to the knob, question, go to the knob, go to reports, and open the DCM derivative report. So when you open this, it will talk to you about all the important concepts that are needed to run this. We did not talk about the cotonians, but really, if you want to get into flight dynamics, Coutonians is the thing to work on. And idea is we don't have to rewrite the code for Coutonian. MATLAB already has the built-in block for the Coutonian that we can use and implement the Coutonian implementation. So if you go down, you can actually open the system. So if you run this section, it will open this BH 6 degree of Coutonian, and then you can actually use this in your code. So this is how that whole thing looks like. You have the sign convention, you have the reference value, you have the command limits, and all that actually goes to the plan. And we are gonna look at that in step-by-step fashion. So I would encourage you strongly to kind of go through this and explore this architecture. Next part is the ODE part. And this is the crux that we spent a lot of time on. I spent 2 lessons talking about the differential equations of motion. This MATLAB script gives you sort of hands-on implementation of what different frames are, how to use the mass inertial properties, how to get these properties in the body frame. Remember these 2 equations that we talked about, the derivative of vectors. So you have a force equation and you have the torque equation. And at the end, you have torque about roll, torque about pitch, and torque about yaw that are used to control the drone. Now, this is the hard-coded Ranjita implementation, which is the 4th order numerical integration. You can use this code or you can use the actual MATLAB code and then generate the results. And you're welcome to run these scripts. And at the end, what's gonna happen is you have the quadcopter model. This quadcopter model is implemented in MATLAB function block, which is in Simulink, which is the body Euler angle fixed mass, and you supply all the property, inertia properties for the quadcopter. This is super important. You supply the values of forces, f of x, f of y, f of z. You supply the torques, p of x, p of y, p of z to this block. And then what you do is on the right hand side, you are gonna get those 12 state variables. Remember velocity, position x, y, z, and then orientations and angular velocity and all that type of stuff. So you are gonna get, and that becomes the output of your simulation. So please run these scripts and that would make your understanding super clear. The next part is, all this is great, but how do we find out the actual forces and torques? To find out actual forces and torques, what we need to do is we need to do some experiments. So what we do is we basically mount a prop on the motor, run the prop at different speeds, measure the thrust, measure the torque, and sort of create an equation using some sort of regression that is used in our control algorithm. So please run through this code, and you can actually use something called as a curve fitting toolbox to find out the equations. Now, I just want to tell you, this approach is so powerful. Let's say if you decide that, hey, I want to build a quadcopter from scratch, you can actually follow this technique. This is called as the model-based design. You can select the motors, do the step-by-step analysis the way we have shown, and at the end, come up with an autopilot for that quadcopter that you can flash on any microcontroller like Arduino or Raspberry Pi, or maybe some ARM processor, and you'll actually have your own quadcopter controlled with your own code. So I would encourage you to take a look at that. So what's going to happen is the torques and the forces that we calculate from experimentation, and the experimentation is also discussed, will get fed into the Simulink file that we are constructing. Next part is the electrical motor modeling, and we spend some time on how the electrical motors are modeled. So electrical motors are modeled using the mechanical subcomponent and the electrical component. So these are the block diagrams for the mechanical component and the electrical component. And if you go down, please run this code wherein there is some experimental data that was collected from some motors that is given, and then it shows you how to actually calculate those motor constants from the experimental data. So if once you run this code, then you can actually use this for parameter estimation of the motor. The next part of this code is we got this model. This model is a nonlinear model. It's very difficult in actual practice to control a nonlinear model. So what do? We simplify the model. And what is the process of simplification? The process of simplification is called linearization. In robotics 1, we talked about the process of linearization. I give you a very simple example. Sine theta. Sine theta is a sinusoidal curve. But as long as the theta is less than 17 degrees, you can use the approximation sine theta is equal to theta. That is sort of the linear approximation of this nonlinear behavior. So you do something called as the linearization. PID control that we are talking about is a linear technique. So linear control may not control the nonlinear system over the entire range of operation, but linear control would control the nonlinear system in a subset of operating range where the behavior is mostly linear. So I would encourage you to look at this, and in this model, we look at the aircraft frame. So you can do linearization about a fixed point, or you can do the linearization about a trajectory. So you can construct a linear model that is valid at say 0, or you can construct a linear model that is valid when value of x is remaining say 1. So depending upon what you want to do, you perform the linearization. In the case of aircraft, a linearization about the fixed point does not make sense. What do I mean by, if you have an airplane, what do I mean by linearization about the fixed point? Which means aircraft is not moving forward, going upward, going downward. So which means aircraft is stationary. That linearization is fine, but that is of no use to us. So linearization is done about an operating point, which means, for example, if the aircraft is in level flight, you would do the linearization when the aircraft is in the flight. Or if the quadcopter is hovering at the steady state, you would do the linearization when the quadcopter is hovering at non-zero z value. Everyone understood this? You can perform the linearization. You can construct a linear model when x is equal to 0, y is equal to 0, z is equal to 0, x dot is equal to 0, y dot is equal to 0, z dot is equal to 0. But for quadcopter, we do linearization, or for airplane, we do linearization at some operating point when the aircraft is in motion. And that process is called as trimming. Have you flown Tello? There is something called as trim. Have you played with the trim command? So basically what that trimming means, that if your Tello is sort of hovering stationary, then if you were to trim it, it would stabilize the Tello at that operating point. So it would change. So basically just look it up. Trimming an RC plane, trimming a quadcopter. Trimming is stabilization when that aircraft is moving. So constructing the linear model. Next part is how do you implement the control? So if you go down this actually talks about the same PID controls that we studied, the steady state model. How do you linearize a Simulink model? So the command for linearization is linearize. And then it actually walks you through the process of linearization. And then you can find the individual transfer functions or the relationship between the inputs and the outputs and implement the control algorithms. So I will spend some more time on this later. But what I want you to do is, I want you to understand that this is the process of model-based design. And then what you do is you go for the full model where you have the linear control, but that linear control is kind of implemented with the nonlinear plant model. And if you look at the nonlinear plant model, this is the big nonlinear plant model that you actually deal with. And we will talk about this in more detail in next class. But at the end, here is what happens. So once you go to the code generation, so what you can do with the code generation is, and I will show you in just a second, you will have to convert the continuous controller to the discrete states. Why you have to control the continuous control in the discrete? Because microcontroller is a discrete system. It's not a continuous system. So what you do is you take the controller block that you have designed, convert that into a discrete controller block, right click onto this control block, and then can you see C++ code? And then what you can do is you can actually build this subsystem, and the MATLAB would create the C code for you. And if you have the Arduino toolbox for MATLAB, you can actually take this C code and flash it onto your Arduino, and that Arduino will behave or work like your flight controller. So it will go through it. So the green line shows that the update rate at 50 Hertz, because please understand, microcontroller cannot run at the speed at which the simulation is running, because it's a CPU microprocessor. So it will actually, once you run through this, it will actually build and create the C code. So this is, I would encourage you to play with this simulation, and we are going to look at this again in next few lessons. So with that, I want to start with Parrot Mambo demonstrations. First and foremost, Parrot Mambo. Have you had success in installing the custom firmware on Parrot Mambo? So I'm gonna, give me a minute. I'm gonna minimize those windows. Okay. So step number 1, go to Simulink. Oh, MATLAB crash. So go to Simulink. Simulink. Online students, can you see my screen? Okay, so go to Simulink, and in Simulink, what you should be seeing is you should go down and you should be able to see the Simulink toolbox for Parrot mini drones. So Simulink support package for Parrot mini drones. This is what you should be seeing. There is something called as the flight simulation template that you can use. There is something called as the hover Parrot mini drone template that you can use. There is something called as the code generation template. So just click onto the code generation template. Now this is hello world of Parrot drones. So before you run any code, this is the first code that you should run. So what are we going to do? This is the Parrot drone that I have. Now what you need to do is, and please don't connect your Parrot drones. Let me show you the demonstration and then I will give you time to do it. So first, what we need to do is we need to connect a personal area network with the Parrot Mambo. How do we create the personal area network? So power on Parrot Mambo. Parrot Mambo powers up. Assuming it has the correct firmware, the eyes will start blinking. Eyes will start blinking. Go on to the Bluetooth, right click, go on to the Bluetooth, right click, join a personal area network, then add a device. So it found a device. So 850160. 850160 is the same code of the Parrot Mambo, which is inside the serial number of the Parrot Mambo. So please connect to your own drone, not to anyone else's drone. Then, how do we check? Pull and see. Connect using access point. And you should see connection successful. Everyone with me so far? Once the connection is successful, what you should do is, you should go here and say build, deploy, and start. So once you do, what did I do?
You have to go to modeling.
Modeling.
Modeling settings. Model settings with the gear icon.
Model settings?
No, the gear icon. Click on the gear icon.
This icon?
Gear.
Yeah.
Hardware settings.
Oh, yeah, hardware board.
And manual. Yeah. And okay. And now we can see him working on labs.
You're awesome. So basically, what I would go to hardware, deploy.
The same.
So what I will do is.
Oh, sorry, you tick on the forgot.
What?
We had to tick modeling.
Hold. Parrot Mambo arm compatible.
The three dots over there.
Let me see if it is still connected, because if it is not connected, oh, it's connected. Okay, yeah.
Click on the three dots over there.
Which three dots?
Three invisible dots over here. Yeah. No, this one. Three dots over here.
Yeah.
And go down.
Uh-huh.
Go down. Click Simulink code features. No. Yeah. Use Simulink code features. Okay. Oh,
and then deploy.
Yeah. Then click on both. Hit enter. Three dots. Oh, it is different.
Which three dots?
No. Go down. Click on both. Okay. Apply. Okay.
So if this doesn't work this time, then I'm going to pull my code and then I'll just run my own code.
You didn't deploy it. You played it.
Okay, yeah.
No, pull out your own code.
Okay. So just click open system, Parrot getting started. Okay. Oh, okay. I did the code generator in the previous.
Go to join functionality. Right click on it. And it will say design
So, yeah, actually, I did the code generation earlier. That's why it conflicted. So let it open. It will create the tool chain. Then you can go to personal area network. Just make sure that it's connected, and then deploy. And deploy and stuff. Yeah, so what happened was in the last set, when I was trying to show you, I used a Simulink coder, and actually I ran the coding. So that's why those files were in the cache. So it didn't work. But now give it a minute. It will actually run. Can you see it gives me ready? Working? Okay, just a second. There are two things here that I want to talk about. You can actually use the simulation stop time, or you can actually decide or specify the time, like 10 seconds, 50 seconds, 30 seconds. And then what you do is, don't run it at very high RPM, high speed. Just say click start. And it will actually rotate alternatively. It will spin alternatively. Can you see?
There is much more easier way that was given.
Much more easier way.
Like it's just one line play.
Yeah. So probably it would work. Then what you can do is you can actually look at the flight log, and then this flight log will get downloaded to the current directory. So you can actually see the flight log. I would encourage you to start this. Let's quickly look at what this code is about. So this code is about getting the motors output. And I want you to actually look at these different states. So you have DCX, DDY, DDZ, PQR, altitude, battery percentage, etc., etc. What you can do is you can modify this code, something like this. For example, you can take this altitude, remove, go to Simulink, library browser, commonly use Box, and go on to the out. So you will have this out. You can actually connect this to here. So what you can do is this altitude sonar can be connected over here. Now, what does that mean? So Parrot Mambo has an ultrasonic sensor. That ultrasonic sensor is going to measure the altitude based on the reflection time and the speed of the ultrasonic or the sound wave. What you can do is go here, and then can you see here there is altitude sonar. You can actually what you can do here is you would be able to, you can go to simulation, go to Simulink browser, you can grab the scope, put it over here, connect this scope to the altitude sonar, and now again deploy the code. So basically hardware, deploy and start. The code will compile, code would get flashed onto the drone. You can open up the scope, open the scope here, and then you can actually start. And then you will get the output here. So probably you need to click the external variable. I'll just show you how it runs. So altitude examples, SLX. Actually, let me open Parrot getting started here. Yeah, actually, I'll run this a little bit later. But so at the beginning, let me say start with Parrot getting started SLX. Yeah, so it has a Simulink catch. So what you can do is you can actually tap into the Parrot Mambo's the rate and all the sensor data. So I would encourage you to do this exercise. The next thing that I want to talk about, and that is kind of a little bit important, is go to again to Simulink. Go to Simulink support package for Parrot, and there is this Hover Parrot mini drone. So Hover, I'm gonna call this Hover class. So now what I want to show you here is, this is the quadcopter simulation model. And in this quadcopter simulation model, this is the flight control system. This flight control system, if you double click, it has the image data, vision-based data, command reference that goes back to the flag. You have sensors, you have the image data, and then what you have is, this is very important, you have the signal builder. So what you can do with a signal builder is you can actually connect it to the joystick, or you can actually connect it to the AC command, or you can actually build a signal. So for an example, check this out. I want you to double click on the signal builder and see what is happening. X is at 0, Y is at 0, Z is at minus 1.5. Please note, minus 1.5 is going up because north is down, Z is going down. So minus 1.5 is gonna go up. Satvik, you might wanna sit back. Now what you will do is, you can actually run this simulation, and I want you to observe what happens in this simulation. So it will actually run and it will show you on screen how the quadcopter is supposed to behave. It can go to minus 1.5 and start hovering. So you'll see that in just a second. Can you see that the quadcopter went on to minus 1.5 and started hovering? Now what I'm going to do is, this is the model that we have built. Now I'm going to stop this. Stop this. Go on to the project. So back. Flight control system. So we will go to the back. Parrot minion hover. And now what I'm going to do is, I'm going to flash this code onto the Parrot Mambo drone. So bear with me just a second. So I would go here. I would actually generate code. Then I would actually deploy. So that code that we actually saw in simulation is actually being built into C and Hex file, and it will be flashed onto the firmware. It's wirelessly being flashed. And assuming everything is successful, you would see that familiar screen for the takeoff. This is the screen that you should see. That means the code built successfully, code got flashed successfully. Now let's see. That is what happens. Online students, you are missing all the fun. Then click land. Stop. Now, if you want to make changes, what you can do is, you can also go. So I just want to tell you, remember the line follower algorithm I talked about, or the code for tracing I talked about? That algorithm would fit here. So what you would do is you would do XY translation, get the image, do the thresholding, and then find out the set the parameters so that basically it's tracking that color. So when I say line tracking, you can actually first I would draw a blue line and then make sure the drone is tracking that blue line. Then actually I will convert that into a triangle and make sure that the drone is able to transition. The other thing that you can think about is if you want to go back to the code, this is the blank code, but there is a sample code which is called MATLAB computation. I'll show you where that is. MATLAB examples, go to Parrot Mambo examples. There is, you can deploy this code, Parrot Mambo to detect objects. Actually, you can also do the waypoint. You can do the path planning. And there is a code for MATLAB Parrot drone computation. So basically, there is a built-in code that you can use. So Parrot mini drone competition start. Okay, good. That's what I was looking for. Thank you. Parrot, small m. Capital. Mini drone. Garbage. So this big file would open and you can actually directly deploy this guy onto your Parrot mini drone. And what it does, it basically tracks an L. So you can actually modify this script, the code to make it track circles or, yeah, actually I would have problem because I already have a flight control system SLX in the memory. So I will have issues, but so it won't close because right now, so this is Parrot mini drone competition start. Okay, let me copy this. Bear with me for a second. Okay, I'll open MATLAB again. Paste. And this folder, this project will open. And this entire code can be deployed directly onto the Parrot. So first, what you can do is you can simulate. Let that code open. So what you can do is you can simulate and view from quadcopter camera. Isometric. Yeah, it's running. It will run. This actually is a very good code, piece of code. Okay, and if you need some help, Tatwik, will you be here? Tech 162 Friday. Okay. So
They're not paying me.
hmm?
They're not paying me.
knowledge. So this is the simulation. Okay, you can deploy this whole code, generate code. Yeah, and then basically you can deploy this code onto the Mambo model, and then it should work. Okay, so I need to stop this. Stop the simulation. Stop. Go back. Go to the project. Set Mambo model. Then generate code. Set Mambo model and generate code. So let's see if there is something blue.
Arrange mass symbol.
What is your massive blue?
Arrange mass symbol.
And assuming the code works, the same, same interface would come. So what I'm going to do is start. So now it stopped because there is a fail-safe logic that tells the drone that when the drone is not actually flying, it will stop the motors. So basically it stopped. Now what I'm going to do is let's see if this works. Can you see error detected in altitude? I told you, don't sit there. So it's trying to detect for the blue. Okay, be careful. Of course. So you are welcome to, that's why I asked for everyone to wear safety glasses. Something like this will always happen. Okay, with that, I'm going to stop here, but you have 5 minutes. So if you have any questions, let me know.
So the parent Mambo that I got from eBay, one of the motors doesn't work. Is there any way that
Yeah, you can contact that guy and ask him to send you a request.
Yeah, so the thing is, it's not showing up on eBay anymore. Even if I click on like find orders and stuff, I couldn't find it.
That dude is here. Yeah, just tell him, send him a picture. MS is good, right?
Yeah.
Yeah, just tell him that got it, it's not working.
And one more question for the final project.
Yeah.
I was planning on taking the machine learning one for the fire detection. That has to be a group project, right?
Which project?
The fire detection in the
Yeah, it has to be Aerospec project, has to be a group project.
So, do we get to contact the Aerospec?
Yeah, next week.
Yeah, because I need some data for the
No,
machine learning.
so basically, you have to sign an NDA and then
All right. So
it
next
will,
week.
yeah, after spring break. Thank you.
Professor, do you want this? I'm just going to throw it away. I ordered it. It's missing sensor.
What is it you say?
It's if you look down here at the bottom, it's missing everything that goes in there. There's no power button. No. I tried.
What?
Yeah,
Where did you order this from?
eBay.
Same seller?
I believe so.
This is
but
the guy,
it's-
right?
it's been
Because
a
he's the
while.
one. So just ask him for a replacement. Then give it to him and ask him for a replacement. Then give you a replacement.
Okay. All right. So just okay. Message.
Just email him and tell them that I'm part of Dr. Edgar's class and we order this and this is missing this. So send us a replacement.
Okay.
Yeah.
This was a drone you gave me on Friday. It has the same issue on a different motor.
Is it working or not working?
One of the motors isn't working. It's a different one from the drone that I have.
Wow, we have a different issue.
So I have ordered some replacement motors, but if you're gonna
Okay.
stop by, I will give you a different motor. But my suggestion to you would be come with your computer, program it there, make sure that the drone is working, and then take it.
Okay. What day should I come by?
Uh, can you send me an email?
Yeah.
I'll let you know.
All right. Thank you.
Yeah.
This was an issue that we've been having with our drone. Like, so when we turned it on and stuff like that, installed the battery, we didn't realize it until we put on the propellers. But this motor seems to be turning on by itself and just spinning. And then, yeah, and then if we try and connect it to an app, like an actual.
Correct. That means the firmware is not properly loaded.
Wait, what?
The firmware for this guy is not properly loaded.
Well, we properly flashed it the first time, and then when we put on the
So
motor.
basically, if you stop it, it stops. That means it's okay. You can actually program this.
Yeah, because we've tried using the app
What app?
from like the one that Parrot released to try and control it. See if that's wrong.
Once you change the firmware, you cannot use Parrot app.
Okay.
You have to use this with MATLAB.
So that means
Now you
it was
cannot
never
control
flashed,
this.
We can still use the Parrot.
But I can tell you that that is normal.
Oh,
You stop.
Yeah, it happened with me as well.
That's normal.
All right.
Let's try it.
Let's
Let's put it on the ground outside. I want to see what happens.
Dr. Someone would show some interest for the Project 6.
What is that?
It is designing. It's an aerospace project, but it's about making a jig, something that stabilizes. Let me just read it out.